Back to part 5 of Yang-Mills standard model, all kinds of good stuff about quantum field theory. I want to talk about the distinction between matter on the one hand versus things like light and forces on the other. As I said, the original understanding was that matter, like in the very early part of the 20th century, matter would be made of particles, although then they discovered that they sometimes behave like waves. And whereas forces were fields, and I talked about how quantum field theory unified those, basically, so that everything could be thought of as a field, everything could be thought of as a particle, everything is really a field behaving like a particle, an excitation of a field that's unexpectedly discrete. So what's the difference? There does seem to be still a difference between matter versus forces. An electron seems to be stuff, whereas photon seems to be something that does something, or that makes the matter interact with each other. Well, guess why they're different? Well, you can see on the slide. It's symmetry. Once again, symmetry is the explanation for something that you wouldn't think needed any explanation, but now we need one. Why is matter different from force? It turns out that if you look at rotating, especially rotating is the essential thing here. There's lots of other symmetries we talked about, but rotation has some very interesting properties. And it turns out that if you look at an experiment and then you rotate the experiment, or especially if you rotate your frame of reference for that experiment, then the certain different kinds of fields transform in a different way. It's kind of like the difference between if you have a point, a dot, and you look at it from all directions, it'll look the same. Or if you look at an arrow, that does look different. Or if you take the arrow and you rotate it, it rotates in a particular way, that the tip of the arrow and the tail of the arrow rotate opposite each other. A dot or an unmarked sphere, for example, if you rotate it, you can't see any difference. There's actually various other ways that patterns can rotate in 3 dimensions, and they go by the name of spin. There's a number you can attach to that. I'm not going to say really any more about the details, but there's a number you can attach to it, and it's called spin. And the most important distinction, it comes in either integers or half an integer. And the most important distinction is that it can either be an integer or a non-integer, just half an integer. So 0, 1, 2, or 1 half, 3 halves, 5 halves. It can't be negative. And it turns out that fermions, this is named after Enrico Fermi, fermions are the ones with half integer spin, and bosons, named after Bose, are the things with integer spin. And well, who cares? Why is that such an important distinction? What does that have to do with matter and forces? Well, it turns out that looking at symmetry, putting that together with quantum mechanics and relativity, you get a very beautiful mathematical statement called the spin statistics theorem. It says that the way a particle transforms under rotations, in particular this number called the spin, how it behaves with that rotational symmetry, affects how they behave with each other. So if you have a bunch of particles, or even 2 identical particles, like 2 electrons near each other, they're going to behave very differently from how 2 photons behave near each other. Basically, just because they obey this different kinds of rotation. It's a very profound and unexpected thing that there's this connection. And it was one of the most important things discovered about the basic structure of quantum field theory. Fermions obey what's called the Pauli exclusion principle. Wolfgang Pauli had already figured this out before the spin statistics connection was really completely understood, I think. But it said that no 2 identical fermions can be in exactly the same state. So if you have 2 electrons, so a very classic example of this is that if you have 2 electrons around an atom, in an atom, sort of whizzing around the nucleus, well, you don't want to picture it exactly as whizzing around like orbits, like you often see in a diagram. That diagram was only useful for a few years, and very soon people figured out that it wasn't really correct. What you really want to picture is an electron cloud around the nucleus. And you can't have 2 electrons having exactly the same shaped electron cloud around the nucleus if everything else about them is the same. And so what that means is you can't pile up matter on itself and squeeze matter together in a way that makes it all try to be in the same place with the same properties. And that's what makes matter matter, basically, is that you can't squeeze it down arbitrarily. Matter likes to kind of have its own room, have a little bit of wiggle room, each particle tend to not want to be near each other and have exactly the same properties. Bosons are very different. They're more gregarious. They like to be in the same state. There's lots of reasons that they might not be in the same state, but there's actually a tendency for them to be in the same state. And so, for example, a laser is something where you set up conditions inside a material so that photons tend to want to get into exactly the same state. And so you can think of it as the standing wave picture. I won't go back to it. You can think of that standing wave picture from a couple of parts ago, that you have not just the fundamental oscillation, but higher and higher and higher oscillations. The wiggles get bigger and bigger and bigger and bigger, and they're all sort of working together to make those wiggles bigger. Superconductors also work in the same way. You get things to sort of trick things to pretend that they're bosons and that they work together. And it turns out that all the force field carriers are bosons. So, for example, photons are the simplest example of a boson. And so that's one reason why forces are very different from matter. It's really based on this spin statistics thing. So I think it's really beautiful that it really comes from symmetry. At least part of it's from symmetry. Let me talk about a few other things about symmetry that I kind of hinted at way back when I started talking about what may or may not be fundamental symmetries of the universe. One of them was mirror reflection. Originally, this was thought to definitely work. This was a symmetry of nature, that there wasn't any reason people could see why, if you built one experiment and then somebody else built a mirror copy of that with everything, all the right-handed screws changed to left-handed screws and the writing is all hard to read. Well, there's no reason people could see that that would give you different answers. But in fact, there's some very profound handedness or left and right-handedness to nature, as far as we can tell. It's really one of the most sure things we know about the universe now, is that there isn't a perfect symmetry. Turns out that only one of the forces of nature, the weak force, the weak nuclear force, is something that has this handedness to it. And it's really, I don't think it's completely understood why that's true, but why is a pretty tricky question. The mechanism is, a lot of that's pretty well understood. So that was a big surprise. Time reversal. And again, this is a tricky one because you don't want to picture like crystal goblets falling to a floor and crashing to a million pieces, because that gets into issues of what if you have many, 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 many things and probabilities. You want to think about billiard balls, or really about electrons and positrons and protons colliding together. There, people were looking at the physics, looking at the equations, and it seemed like there was no reason that there's no way to tell whether the movie was going forward or backwards. That time reversal was a symmetry of physics. But it turns out, again, not quite. Now, this one's very, very close to working. And this one might relate to some of these other mysteries. It might relate to things like the composition of matter in the universe. It's still a very active research topic. And one reason is that it relates to the next one, which is charge reversal. So in classical electrodynamics, electricity and magnetism, you can look at the equations and you can say, okay, if I had a bunch of negative charges, they're going to behave in a certain way. And if I flip all the charges, they're just going to behave in exactly the same way. But the interesting thing is that once you start looking at the content of the universe, you discover electrons and protons. And they're very, very different from each other. Electrons are much, much lighter, and protons are much, much heavier. There's no symmetry between them. So you have the electrons, which are negatively charged particles, and there doesn't seem to be anything, there wasn't expected anything that would correspond to a positively charged electron. But in the late 20s, early 30s, Dirac predicted that, in fact, there should be positively charged electrons. It's just that we don't seem to happen to have any of them naturally. But when you start doing collider experiments, you get this, and it's called antimatter. And antimatter kind of has a real sci-fi reputation. There's nothing weird about antimatter. It's exactly like ordinary matter. It's just that the charge is reversed, and some of the other stuff is reversed about, some of the other properties are reversed. It's just that the only thing that's weird about it is that we just don't have any of it around naturally anywhere in our universe as far as we can tell, or the ratio of matter to antimatter is an enormous number. And so it turned out that At first, people didn't expect there to be this symmetry because we didn't have positively charged electrons. Then people discovered positively charged electrons and negatively charged protons, for example, antiprotons. But then, again, people discovered, well, it's not exactly a full symmetry. So these are some weird stories about parity, time, and charge. There's some weird things here that get into some real deep stuff that it's really important to think of these symmetries as possibilities. But it turns out that the deviations from symmetry are really the interesting part of the story. Now, it turns out, to rescue some symmetry and some good news for symmetry here, is that if you do all three of these together, you take any experiment and instead of, in that experiment, change all the particles to their antiparticles, change all the charges. Do a mirror reversed version of it. Change any kind of left-handed spinning to right-handed spinning, for example, and play the movie in reverse. Then that should make sense. That should correspond to a physically possible experiment, and it should be an exact symmetry. It's another one of these theorems you can prove from the space-time symmetries of special relativity. You combine that with quantum mechanics, and it really just pops out mathematically. And so people would be very, very surprised to find a violation of CPT symmetry, because people very strongly believe in the basic symmetry of special relativity. That's very well tested, and it would be very surprising to have a breakdown of this. It's not impossible, but it would be unbelievably a huge deal. It would require a huge modification of the basic ideas of physics. So far, roughly 1950, although this is not supposed to be historically accurate or chronological, we've got a beautiful theory of quantum electrodynamics. It's based on quantum field theory. The way people calculate with it is with Feynman diagrams, although I'll say more about exactly what's going on with that. What I wanted to mention, though, is the subtitle of this whole presentation is a Jekyll and Hyde story. Well, we've seen the good part, the Dr. Jekyll part. What about Mr. Hyde? Well, we'll see that very soon. Quantum electrodynamics is based on quantum fields with local symmetry. Everybody has this little clock. Every point in space space and time has this little clock running. But it's only the simplest kind. I've shown you that when you think about symmetry, you think about rotation especially, just rotating a circle isn't the most interesting kind. You could rotate a sphere, for example. And what's different about that, what's more interesting about that, is that the order of those rotations does matter. So in the QED theory, quantum electrodynamics, we're using only the simplest kind of symmetry. And then what the experimental situation, or the more physics situation, as opposed to just the pure math of the theory, what needs to be explained? Well, the strong and weak nuclear force had shown up for at this point, they'd been around in some way for many years, decades, and there wasn't a great explanation for those forces. There wasn't a coherent explanation that really understood everything, and we'll see a little bit more about the problems with that. And of course, there's lots of other things, like how do you quantize gravity? That's this kind of stuff that's beyond the scope of this talk, because it goes beyond the standard model. But there's certainly stuff that needed to be done. Well, on the theory side, Yang and Mills come together, and Yang-Mills is the titles of these things, because it turns out that their kind of theory has come to dominate, but I want to talk about why. In 1954, they proposed a quantum field theory with non-abelian local internal symmetry. So remember, the local means that everybody can adjust it independently of each other. The internal means you don't want to think of this as actually taking up your experiment and moving it in some way, that there's some sort of formal mathematical thing that you attach to every point in space, or you can think of it as maybe as attaching to the particles, and that's what's getting adjusted by the symmetry. And then non-abelian is a fancy word for saying the order matters. So a way to picture that is sort of every particle or every point in the universe gets a spherical clock, and they can adjust them all relatively to each other. It's a beautiful, beautiful theory. It's mathematically wonderful, and it turns out to dovetail a lot with what mathematicians were thinking about at the same time, although it took 20 years for them to start talking to each other about it. But here's what's one of the things that's wrong with it. It's too much like quantum electrodynamics. One of the things about QED is that the photons have no mass. A photon is a massless particle, and that's fundamental for relativity. It's fundamental for how QED works. And the Yang-Mills theory would have predicted, without any modification, that the carriers of the strong and weak nuclear force, which they were trying to explain, would also be massless. Well, what's wrong with that? Is that a problem? Well, it seems like that would give long-range forces. It turns out that the range of a force has to do with the mass of the carrier for that force. And in particular, a massless force carrier gives a force that decays pretty slowly as you separate two particles farther and farther apart from each other. The thing about the strong and the weak forces, though, the reason they're called nuclear forces is that they're relatively strong. Even the weak force is meaningful and operates at nuclear scales, but it becomes very, very weak if you go a little bit beyond that scale. And so it was really, really a horribly wrong prediction. So part of the answer, I'm not going to tell you about all of the answer for that, but especially for the weak force, part of the answer turns out to come from what's called symmetry breaking. So broken symmetry, let's talk about that. So you might think that you've got this beautiful theory, the Yang-Mills theory. It uses symmetry in a beautiful way, like QED, but it was too much like QED. So maybe symmetry isn't the answer. Well, it turns out that you don't get rid of it. You kind of hide it. You partially hide the symmetry, and it's called symmetry breaking or broken symmetry. And it starts out in 1960. People had the first proposals of this. The idea is you let the physical laws be symmetrical, but you assume the universe is in an asymmetrical state. A common analogy people like to use here, because it has some real interesting similarities to the theory that really gets proposed, is like a ferromagnet, like the kind of magnet you have for a refrigerator magnet. Turns out if you take one of those and you put it in a really high temperature oven or a kiln or something, then it will demagnetize. And here's why. The way a ferromagnet works is that at low temperature, you've got a bunch of iron atoms, and their spins are lined up. They're like little tiny spinning bits of current you could think of. And I've got arrows here to denote the axis of their spins. And at low temperatures, they tend to line up. At high temperatures, you're putting a lot of energy into this material. And of course, temperature is because it has to do with the bouncing around and the excitations of the atoms in any kind of material. And so at high temperature, those spins tend to disalign, and they can't help each other to produce a large magnetic field. And so how is this a symmetry statement? Well, at high temperature, this is actually it looks kind of crazy, but it's a fairly symmetrical picture. If you had 1,000,000 spins and they're all going in random directions, then there's no preferred direction. It really kind of looks the same if I rotated it. But here, this would look very different if I rotated it. This is all the spins are going up. And so it would look very different. Or another way to say it is if I were a detector, if I were an ant in here, or some sort of small-scale detector, and I wanted to know, can I tell which way the field is going? Absolutely. It's definitely going up, and I can tell the difference between the up direction and other directions. That's a less symmetrical picture than this picture. Other examples of broken symmetry, for example, a square sheet of paper. If you look at a plane, a mathematically idealized plane, that has a translation symmetry. You can translate infinitely far in any direction. A square sheet of paper breaks that symmetry because there's an edge to the paper. And you can't just, if you're an ant, you can't just walk forever and say, oh, basically everything's the same. When you get to the edge, you notice it. And so that kind of breaks the symmetry. Also, it breaks the rotational symmetry down. If you had an infinite sheet of paper, you could rotate it by any angle. The square sheet of paper we've seen, we can only rotate it like 90 or 180. A buckling plastic rod. These are good. I got some of these examples from the Wikipedia article on broken symmetry. There's a nice list of examples. If you start out with a perfectly symmetrical plastic rod and then you squeeze it, then it's going to buckle in one direction or another. Just by some sort of minute instability in the rod, it's going to choose a direction. But if you don't shatter it, you just buckle it a little bit. One important observation is that it still has that symmetry sort of hidden, that if you let it pivot on these points, it'll swing around and have a circular symmetry. So this thing, the entire thing is a circular symmetry. Here, the object isn't circularly symmetric, but it could have buckled in any direction, and in fact, it's going to be easy to rotate it around to say, oh, well, maybe I didn't want it to buckle in this direction. I want it to buckle in this direction. It's going to be very easy to just spin that so that it is buckled in that direction. Turns out that it has a real good analogy to what happens with the mechanism that I'm going to talk about in a minute. Heating water on a stove is a great example. If you have a perfectly symmetrical stove pot, like a saucepan, most of them are very symmetrical. You heat the water on the stove, eventually bubbles form, and the heat comes up from the bottom to the top and circulates around in what are called convective cells. That's another broken symmetry. Okay, so let me just do one more slide and then I'll break it. So in 1964, Higgs and a lot of other folks, about 6 or 7 people, depending on who you talk to, who get credit for this. It was an explicit mechanism. It's much more explicit than this basic proposal in 1960. An explicit mechanism and a new field that breaks the symmetry of a Yang-Mills theory. And it would give the Yang-Mills force carriers mass. And in fact, it gives everything a mass. That sort of the reason things have mass is how much they link to this new field, the Higgs field. Well, if we have a new field, we had to put a new field in to have some sort of mechanism to break the symmetry. Anytime you have a new field, that's going to give you a new particle. What if you excite that field in particular? If you make that field bump up and down. So the main use of the field is its interaction with everything else. The fermions, which are the particles, and the bosons, which are the forces. But what if you actually were able to make that field wiggle up and down on its own? You should create what's called the Higgs boson. And that's not how you spell search, is it? Oh well. The Higgs boson is the one big piece of the Standard Model that has not yet been observed. It's the #1 physics priority. And at the Large Hadron Collider right now, as far as I know, I checked a few minutes ago, they're colliding protons at super high energies right now. And they're very much wanting to create an unmistakable signature of the creation of a Higgs boson. But I have to mention that it sometimes gets called the God particle in like news reports and things. Somebody came up with that, and it's absolutely the worst popularized name ever. It's a horrible, horrible name for that. Okay, this is a good place to break